Okay, in this video we're going to take a look at our new module, Unit 3.2 Probability. So I'm going to go to the Materials section. We'll look at some of the materials, including the text and the homework together. So I could click here, or alternatively down here in the schedule. Okay, so description, we're going to take a closer look at errors in reasoning about probability. And that's our real focus here, errors in reasoning about probability. You're not going to be asked to do a lot of probability or any complex probability calculations on your own. Most of the calculations you'll be asked to do will be guided, and our emphasis will be on the kinds of errors we make when we reason about probability. Now, some of this material is going to seem familiar because we already saw errors in reasoning about probability in our unit on cognitive biases. There we looked at the representativeness heuristic, and that included reasoning about probability in a bunch of ways: the conjunction fallacy, base rate fallacy, regression to the mean. We're going to see those same kinds of errors in reasoning about probability in this material. We're just going to look at them more deeply from the perspective of probability. We're really going to get at where they go wrong probabilistically. And you're going to see it again in the fallacies section. We'll have the base rate fallacy as one of our 8 fallacies. So one thing you might wonder is, what exactly is the difference between a cognitive bias and a fallacy? For what it's worth, here's my super short take on it. Both are about errors in reasoning, but what we mean when we say reasoning can mean two different related things. One, imagine your head is a black box, and the claimant information comes in and conclusion comes out. And whatever happens in the middle is something that has to do with how your brains work, right? And call that thinking or reasoning, right? Info comes in, conclusion comes out, you have reasoned. And when we defined cognitive bias, it was a tendency to reason in a way that produces a predictable error. So we can reason about probabilities either by stopping to see how easily we can think of an example, or to compare with what seems typical, again, thinking in terms of examples. So that's a kind of thinking that we can engage in that will predictably lead to errors in certain kinds of contexts. So that's one way to think about reasoning about probabilities as an error in reasoning. What's going on in your head? Are you thinking of examples, or are you reasoning in accordance with the laws of probability? Another way to think about reasoning is what we can represent in standard form, right? Not what's going on in your head, whatever's firing and producing and comparing with examples, black box. But instead, what we can spell out in an argument. In the fallacy section, we are looking at arguments. We're not imagining how a person could be thinking, what could be going on in their head. We are looking at arguments. And we'll be identifying where there are errors in an argument and an inference from certain kinds of premises or whatever. So that's our essential difference between cognitive biases and fallacies. And both of them are connected with reasoning about probability, and the whole point of Unit 3 is to sort of focus in on kinds of reasoning, like reasoning about statistics, probability, and causation in a little bit more detail. So this is really closely connected to the fallacies unit, just highlighting more closely what it takes to reason about things well and why exactly what we look at as errors are errors. Okay, so we've got our learning objectives here. There are some notes, a guide to the module materials. As usual, the text is an essential resource. In this video, we're going to look at it together. There are videos below, and I recommend all of them. And there is a probability primer. So if you are not sure about how to figure out just the most basic probabilities, like what it means to ask, what's the probability of rolling a 1 on a 6-sided die, or slightly more complex questions like that, maybe review the this probability primer. The videos. If I were going to recommend videos for this week, I'd recommend the top 3 and perhaps save the conditional probability tree one for next week, because next week we'll look at those in more detail, which I'll mention when we get to the text here. So let's do that now. Let's open up the text. You should read this little intro page, but I've said most of what's on it already. And let's skip to the first section on the conjunction fallacy. So again, this is something you've seen already. So example, Steve judges that it's more likely for men over 65 to have a heart attack than for men over 18 to have a heart attack. Why is that fallacious reasoning? One thing worth highlighting here is that on its own, this isn't actually an argument. This is just a claim. It's more likely for this than for that. But it might be a premise, maybe an implicit assumption in Steve's reasoning. And if so, then there'll be an error in any argument, any piece of reasoning based on this assumption. And this assumption is problematic. Here's a similar example. Steve judges that Linda, who majored in philosophy, was an activist, an active social justice advocate. We saw the Linda problem early on in our cognitive biases section. Steve judges that Linda is more likely a feminist and a banker than merely a banker. And that is, again, a belief, but if it plays a role in reasoning, it's going to affect the reasoning, because it is a false belief that gets probability wrong. Okay, so both of these judgments violate a law of probability, namely the conjunction rule. And we're going to visualize where exactly it goes wrong. Before we do that, let's just try to explain it in ordinary language. Why exactly these things are errors in reasoning about probability. The basic idea is for any two independent outcomes, so things that aren't themselves related, one doesn't make the other more likely or less likely. For any two outcomes or events, it is not going to be more likely that both of them happen than just one. It might be equally likely that one or both, but it's never going to be more likely that both happen than just one. So for the feminist and a banker, it's not more likely that she's both things than just one. Why? Because how to get to be both things, you have to be one, right? So to be a feminist banker, you've got to be a banker. It's already included in the probability. So being both is not going to be more likely than just being a banker. And similarly, if we say there's this population, men over 18, what are the odds that men over 18 have a heart attack? And when you then break off that population into 65 and over, and what are the odds that they have a heart attack? Now there's sort of two conditions, being in the over 65 category and also being in the heart attack category. So what are the odds that you're 65 and have a heart attack? That's much more specific than being over 18 and having a heart attack. Because the 65-year-olds are already in the over 18 category. You've just made it more specific which category that person is. And so maybe the probability stays the same, but that's the best case scenario. Most likely the probability is going to be lower because now there's a sort of more hoops to jump through to get this outcome or event. That's maybe one way to look at it. So that's the big idea with the conjunction fallacy, and our goal is to visualize it and be able to do the calculations with numbers as well. So all of these numbers are made up. This is like doing a back of the envelope calculation to make a point and not real numbers. I made these up. So say that out of the entire population of men over 18, 20% of that population is 65 or older. So here's 100 dots. And let's make 20% of them, so 20 of them, the 65 or older crowd. That's what the blue dots refer to. Now let's say that the probability that a man aged 18 to 64, so that's any one of these, right? And here I'm gesturing to the black dots. So 18 to 64 are the black dots. So imagine that the probability that a man aged 18 to 64 has a heart attack is 5%. So what is 5% of 80? That's going to be 4. That's why there are 4 red dots, and I just sort of randomly picked 4 of them. 4 out of 80, that's 5%. And imagine that the probability that a man in the 65 plus crowd is 20%. Well, what's 20% of 20? That's going to be 4 as well. So I just picked 4 red dots. So here's our landscape. This is what it looks like for 5% of this crowd to have a heart attack and 20% of this crowd to have a heart attack. 4 and 4. So what is the probability that a man over 18 has a heart attack? Now remember, everyone in the diagram is over 18. So what is the probability? That'll just be the number of red dots out of 100. So 8 out of 100 is 8%. What is the probability that a man is both 65 and has a heart attack? Now we're only interested in this group of people, and that's going to be 4 out of 100. So the probability that you're both, out of all of these people, only 4 out of all of these people are both over 65 and have a heart attack. So that's 4%. And the point is that even though heart attacks are much more common in the 65 plus crowd, 20% is a much higher number than 5%, because there are so many more people in the under 65 crowd, that the percent in each population ends up being the same. Okay, so what if all the numbers stay the same, except that no one under 65 has a heart attack? So what if our stereotype that it's people over 65 are definitely the ones having the heart attack, say? So assume these are all black here. Well, then the probability of being in either group, being any man and having a heart attack, will be 4 out of 100. And the probability of being in this group of people 65 plus and having a heart attack is also going to be 4%. So they could be equal, but it's never going to be the case that the person who meets more criteria, being older and having the heart attack, is going to be more probable than being meeting fewer criteria, being any man and having a heart attack. Okay, so the next bit of the text just focuses on, well, how might we be thinking about this, right? So we're committing a probability error, but how is it we got to there? So if we're asking, like, what's going on in their head, we're asking about essentially the cognitive biases material. Why are people inclined to judge that it's more probable that a man over 65 will have a heart attack than a man over 18? Well, one explanation is the representativeness heuristic. We're assessing probability on the basis of fit or stereotype. Instead of stopping to think about the probabilistic calculation we'd need to engage in, we're asking, does this fit a stereotype? Old people, heart attack, check. Checks out. Everything checks out. I don't need to think about this any harder. Another possibility is that there isn't any kind of cognitive bias going on here, that they're just implicit assumptions about like what's being asked. So maybe Steve is assuming that when somebody says man over 18, they're meaning like man between 18 and 64 and not including the older population, and that would remove the error in their thinking about probability, but there's reason to think that that's not quite what's going on, especially in a Linda case, but those are possibilities. Let's move on to the next error in reasoning about probability. Again, another one we've already seen, base rate fallacy. Okay, here's the example. Steve reads the following profile on a dating website. My name is Jamie and I'm a student at UCSD. I'm generally creative and I'm the type of person who has little drive for order and routine. I'm free-spirited, easygoing, inquisitive, and I always try to maintain a childlike sense of wonder. While I do tend to think deeply about the big picture and where I'm going, I can't help but to jump into things spontaneously and with wild abandon. I'm deeply interested in other people, and I like to think I'm generally well-liked. For all my better qualities, I can also be very judgmental, outspoken, and hot-headed. Steve is surprised to find out that Jamie is a biology major. He assumed she was most likely a creative writing major. Okay, so how is this an error in reasoning? He draws the conclusion that she is most likely a creative writing major on the basis of a description of her personality. And it's an error. So what goes wrong here? Well, one way he might be thinking about it is Jamie fits the stereotype of a creative writing major, so she probably is one, right? So it seems plausible that a person who draws this conclusion is reasoning on the base of fit with an example. So if this is a base rate bias or fallacy, he has to be ignoring important probability information and thereby ending up with the wrong answer. So what is the important information that he is ignoring? Base rates. What is the probability, just in general, that Jamie is a creative writing major or a biology major? Independent of anything else we know about her, what is the probability that she is either one of those things? And the answer to that question significantly shapes our reasoning about whether or not she is probably a creative writing major, given this additional bit of information we are given. And when we ignore this base rate question, what are the odds she's a creative writing major at all, that's how we get led into the wrong answer here. And this requires background knowledge. You would need to know that a school like UCSD, this is probably true of most schools, but especially a school like UCSD, where biology is the largest major at this very large school, and creative writing, I don't know what size it is, but I imagine it's a very, very small major. So the fact that there are very few creative writing majors and many, many, many biology majors is relevant to our reasoning about how likely it is that Jamie is a creative writing major, even given this additional information. Okay, so let's, I'm going to sort of skip ahead here. I'm skipping over this probability tree, and I'll come back to it in a moment, and I'll say a bit more about conditional probability trees. But let's just go to an infographic way of reasoning about this, and let's make up some numbers, do a back of the envelope calculation together. Okay, so we've got 100 dots here, and because the math is just a little bit more complicated here, let's let each dot represent 10 students. So this represents 1,000 students, each dot 10 students. Let's say, because we need a couple of probabilities to get started. One, let's just say that 100% of creative writing majors are, and let's call Jamie's personality type extroverted free spirit, EFS. So 100% of creative writing majors are extroverted free spirits. Let's just say that stereotype is absolutely true. The next question we need to ask is, well, what about all of the non-creative writing majors? How many of them fit this extroverted free spirit type? And let's just assume that it's much, much lower. If 100% of creative writing majors are, what percent should we say for the non-creative writing? Let's say 20%. That's fairly low, just 20% of the general population of students who are not creative writing majors also fit this description. And then finally, important, we need our base rate. How many students are creative writing majors? What percentage? Let's say 1% of UCSD students are creative writing majors. Okay, so out of our 100 dots, which each represents 10, 1%, that's going to be this little corner dot here, is a creative writing major. And 100% of those students are extroverted free spirit types. So this blue dot stands for is a creative writing major and is an extroverted free spirit. 10 out of the 1,000 students will fit that description. Now, how many non-creative writing majors are there going to be? 99%. And of those, 20% are also extroverted free spirit types. So that's what the purple dot stands for. This, and we're rounding a bit because of the dot situation here. So let's let 20% of all the rest also be creative free spirit types. And then the red dots, this is people who are not creative writing majors and who are not extroverted free spirits. It's a lot of them. Okay, so how do we figure out what is the question we're asking? We're asking, what are the odds that Jamie has a particular major, is a creative writing major, given this description about her personality? If we weren't given the description about the personality, what we just need to know is, well, how many students are creative writing majors? That's our only information, and we'd say there's a 1% chance she's in this group. But now that we know she's a creative, that she's got this extroverted, free spirit personality type, how does that change our probability assessment of her major? So what do we need to know? Well, we know that how many students in general are extroverted free spirit types. Well, let's just count all the blue and purple dots. And how many of those people who fit this description, this is all the people who fit the personality description, that's 210. Of those, how many are both creative writing majors and extroverted free spirits? So, what is the probability Jamie's a creative writing major given she's a free spirit? The answer is blue dots divided by blue plus purple dots, where 10 divided by 210 equals 0.048 or 4.8%. So when we're given this information about her personality, it does increase the probability that she has this particular major, but not by a lot. Now it's only a 4% chance. So the base rate significantly influences the probability in this case about what her major is or is not. And if we reason purely on the basis of fit with a stereotype or example, we're likely to get it wrong. Okay, now let's take a look at the homework. And while I'm navigating there, I'll say you're going to see these kinds of calculations again in the fallacies section on the base rate fallacy as well. Okay, so homework 12C, probability. Okay, yours could very well look different on a couple of these questions because the questions change with each attempt. There are reminders about the rules, but this is very close to the text. So, visualizing here. This is just like our first example with the 65 plus heart attack example. It's really just going through the same thing we went through in the text and how to answer questions about probabilities to get at answers. So now we're going to do it with a new problem, okay? And again, you might get this one or you might get a different one, but the way we're thinking about it will be the same. So let's assume that we're only considering the population of adult-aged men, 18 plus, and this time let's say that out of our entire population of men over 18, only 10% are in the 65 plus camp. So now there's only 10 blue dots. What this information means is that there's 100 dots, 10 are blue, representing the 65 plus crowd, and the remaining 90 black dots represent all the other adult men who are not 65 plus. Now, let's say that the probability that a man not in the 65 plus range has a heart attack is 10%, so it's higher than our previous example, and that the probability that a man in the 65 or older group has a heart attack is 90%, so let's make it that stereotype extremely true. So here's how we represent that information we were given. P, H, this bar means given, H given not 65. So what is the probability of having a heart attack given that you are not in the 65 plus group? That's 0.1 or 10%. What is the probability of having a heart attack given that you are in the 65 plus group? Equals 0.9 or 90%. And now visualizing that, so this is 90 black dots. What is 10% of 90? That's going to be 9, so that's why there are 9 red dots here. And what is 90% of the population of 10 here? That's going to be 9 out of 10, so you've got 9 red dots here. And that's what this means. Of the 90 black non-65 plus dots, 9 are red, representing the 10% who have a heart attack. And of the 10 blue, 65 plus dots, 9 are red, representing the 90% that have a heart attack. Okay, so what we want to know is, question 1, what is the probability of having a heart attack? What is the probability that a man of any age has a heart attack? Well, out of 100, just count the red dots. Is it 9 or 18? Out of all the red dots, right? And what is the percentage then? That's going to be 18. What is the probability of being in both groups, of having a heart attack and being in the 65 plus age group? What's the probability that a man is 65 plus and has a heart attack? Well, now we're counting just the number of red dots in this group. So that's going to be 9. And our point here is just that this isn't more likely than the whole thing, right? Now let's do the math without the picture. So use this, you can go back up here to sort of find the information you're looking for, but what's the probability that a person is in the non-65 plus in age? Well, what's the probability of being in the non-65 plus group? We said that was 0.9. That's just a number we made up when we were doing the back of the envelope calculation. And what's the probability of having a heart attack given that you are in this group? Again, this was a number we made up. We said that would be 10% or 0.1. So what is 0.9 times 0.1? That's going to be 9%, and that's what those 9 red dots in the top half represented. What's the probability of being in the 65 plus group and having a heart attack? Well, same idea. What's the probability you're in the 65 plus group at all? We made this up. We said it was 10%. And what's the probability of having a heart attack given you're in this group? Again, this is something we made up. We said it was 90%. These aren't real numbers. So the probability we're looking for then will be 0.1 times 0.9, and it'll be 9%. These just happen to be inverse based on how I made the numbers up, not because they will always be that way. Those are just the numbers I made up. The question then is, how do we figure out this probability versus this probability? Because these are the things we're reasoning about, right? So what is the probability of having a heart attack for anybody? Well, what's the probability of being in this group and having a heart attack, or being in this group and having a heart attack? And when we want to know the probability of one thing or another thing happening, we add them, just like we added up all those red dots. And again, the error is that we reason that this thing is more probable than this thing, because we focus on a stereotype instead of the probability information. Okay, next. Here we've got the Jamie case again, but with different numbers. Same idea illustrated with different numbers, different back of the envelope calculation here. So let P parentheses CWN stand for the probability that one is a creative writing major. And so let's start by getting our base rate down. Let's assume, for the sake of example, these numbers are just made up, that 5% of students are creative writing majors, and that's a high estimate. So if we have 100 dots, let's make 5 of them blue to stand for the creative writing majors, and all the black dots are not creative writing majors. And that's what this says here. Now let's visualize some additional probabilities. What are the odds, what's the probability that one is, and remember this bar means given that one is, let EFS be extroverted free spirit, personality type. What are the odds one has this personality type given one is this major, creative writing? Similarly, what are the odds that one has this personality type given they have a different major, any other major than creative writing major? We need to make this stuff up again. So, in order to complete our back of the envelope calculation. So let's assume, for the sake of example, again like we did last time, that the stereotype is true. Assume all creative writing majors are extroverted free spirit types. That means let the probability of EFS bar given CWM equal 100%. And again, let's assume that 20% of non-creative writing majors are extroverted free spirits too. So that'll be P, EFS bar, not CWM. Let that equal 0.2 or 20%. Okay, so in our bar graph, remember below, or our dot plot, below we had these 5 represented the creative writing majors. Well, now we're going to make them red because red means our extroverted free spirits. And let's just make 20% of the black dots also red to represent the 20% of non-creative writing majors that are also extroverted free spirits. Okay, so we've got our whole population of students and how many of them have this personality type and how many are in each major. So question, what is the probability that Jamie is a creative writing major? That's what we ultimately want to know. What are the odds she's a creative writing major, given she has this personality type? To answer this question, we need the following information. Well, how many people fit this personality type at all, whether they have any major, right? So we know that 100% of the creative writing majors have it, but also a lot of other people do. Well, given our back of the envelope calculation, just count the dots here. There's 24 dots. And of these 24 extroverted free spirit types, how many of those people are creative writing majors? Again, that was just our original 5. So red dots that are creative writing majors, 5, divided by total red dots, 24. That's about 21%. So closer to what here? Closer to 20%. Okay, so that's how we figure out the probability. What are the odds that this person is in both camps, has this kind of personality, and is a creative writing major, divided by the probability that anyone having this kind of personality type gives us the answer to our question. And again, you might have had different numbers, but the idea is the same, right? So hopefully this helps you whichever question you get. Finally, we have the famous cab example. This is another base rate fallacy illustration. So consider the following scenario. A taxi cab was involved in a hit-and-run accident at night. Only 2 cab companies, this was before we had Uber and Lyft apparently, only 2 cab companies, Green Cab and Blue Cab, operate in the city. 85% of the cabs in the city are green. 15% are blue. A witness identified the cab as blue. The court tested the reliability of the witness under the same circumstances that existed on the night of the accident, let's just say, and concluded that the witness correctly identifies each one of the 2 colors about 80% of the time and fails the other 20%. Here's our question. What's the probability that the cab involved in the accident was blue rather than green, given the witness identified it as blue? When presented with this problem, many people estimate that the probability that the cab was blue, given the witness said it was, is around 80%. But this is pretty far off the mark. That's why it's an error and we are studying it. So it would be a mistake to home in on this specific bit of probability information, this witness success rate at 80%. We're homing in on a very specific bit of information and ignoring important other information that is relevant in the word problem here. In particular, we're ignoring this more general base information that there are only 15% of cabs operating in the city are blue. So we can visualize this question. Step 1. Let's visualize 15% of the cabs being blue and 85% being green. So here's 100 dots, 85 are green, 15 are blue. Blue cabs, green cabs. And this is the color the cabs actually are. Now we're going to add the witness accuracy information. We know the witness is correct 80% of the time for both colors. So dark blue means witness says it's blue, not it's actually blue. And light blue means it's actually blue. So of these 15 actually blue cases, the witness says it's blue in what's 80% of 15? Just count these dots, 12. So 12 times when it's actually blue, witness says it's blue. Now the other 85, it's actually green, but 20% of the time the witness gets it wrong. So in 80% of the times they'll say it's green and it'll actually be green, but we're only interested in the cases where the witness says it's blue. So how many are those? What is 20% of 85? Well, let's count these dots here. 17. 17 times they'll say it's blue when it's green, and 12 times they'll say it's blue when it's blue. Now, step 3, figure out how often the witness says blue when the cab is actually blue. So what is the probability? What is the probability that the witness correctly identifies a blue cab as blue? What is the probability of correctly identifying a blue cab as blue? Well, that requires first we're in the blue cabs, the actually blue cabs, and then we're in the correct identifying range as well. So out of these 100 possible things the witness could have actually seen, there's a 15% chance what they saw was blue, and of that there is an 80% chance that they got it right, and so we multiply the odds that it is a blue cab and then the probability that the witness says it's blue given that it's actually blue, so we're multiplying, and we get 12%, or 12 dots. So here it is in terms of dots, and here it is in terms of just basic math. And again, these are the numbers that we were just given for our back of the envelope calculation. Next, figure out how often the witness says the blue cab is blue, figure out how often the witness says blue when it's actually green. This is a crucial piece of information that we're likely to ignore. So how often does the witness say the cab is blue when it's actually green? So we could just count the dots here. When it's actually green, we're in this range of possibility. How often do they say it's blue? 17. So just 17 dots. Or we could do the math. What are the odds the cab is green at all? We said we just stipulated it's 85%. And we also stipulated that the witness is wrong 20% of the time, right 80% of the time. So what are the odds that they say blue are wrong, given that it is green? That's going to be 20%. 0.85 times 0.2 is 17%. Okay, so now that we have those two pieces of information, the odds they'll say it's blue and get it right, the odds they'll say it's blue and be wrong. Now we want to know, what are the odds that the witness says it's blue and gets it right out of all the times they'll say it's blue? So what's the probability they say it's blue, right or wrong? That just requires adding all the times they say it's blue, right or wrong. 12 plus 17. We could just count the dots, or we can do the probability information, and that's just adding the two bits of probability we just calculated. So this says it's blue and is wrong, and this says it's blue and is right. We'll just add, what are the odds that either one of these things happen? We'll add those up. That's 12% plus 17%. Now, what are the odds that they are right, given they said it was blue? So of the 29 times they say it's blue, 12 of those times they are right. So what is the answer to this? And as we can see, it's 0.41, so about 40%, closer to 40%. Okay, and again, you might have a different question, but the back of the envelope numbers we assume to be true are what's different. The underlying idea, how to approach the question, is the same. Okay, let's go back to the probability materials. The thing that we skipped that was in the text that we didn't look at is how to use conditional probability tree diagrams. That is something we'll focus on for next week. So in next week's material, you are going to see the CAB example again. We're also going to use tree diagrams to answer the question. And then you're going to get questions about what are the odds that you have a disease given you've tested positive for it. In the fallacies text, let's head to the base rate fallacy in the fallacies text here. You'll see a bunch of examples of where we are figuring out the probability that a person has a disease. In this case, we use Lyme's disease, given that they've had a positive test result. And so this is something we'll look at in more detail next week. We will learn how to use tree diagrams to calculate this, as well as to do it by thinking in terms of frequencies. And that illustrates another point about our reasoning about probabilities. We're much better when we reason in terms of frequencies than when we reason about it in other ways. How that information is presented to us matters. Think framing effects. Okay, that concludes our focus on probability for this week. And I'll see you next week to talk about probability trees and the probability of having a disease given you've tested positive for it.